Hi guys, welcome to the second part of lesson 2, applying the properties of exponents. So these we did at the end of our last lesson, so we're just going to kind of review those. So remember, I'm going to think about that chart from lesson 1, and so I'm going to find the factor of 48. That's the biggest perfect cube that I can find in that chart. So if you look at the chart, 8 is a perfect cube. So 8 times 6 is 48. And so I can take the cubed root of 8. That is going to come out as a 2. And the 6, I can't. So my answer is going to be 2 cubed root of 6. So I'm going to do the same thing with this. So let's think about perfect fourths. So 625 times 2 is a perfect fourth. And then remember, we're going to take, so the fourth, let's kind of take this apart. So the fourth root of x to the fourth, that's the same thing as saying x to the 4 over 4 power. So when I take the fourth root of that, it just comes out as x to the first or just x. So let's kind of tie this all together. So 625 times 2 times x to the fourth. So the 625, the fourth root of 625 is 5. That 2 can't come out, but sorry, this is an x to the fourth. But that 4x to the fourth is going to come out as an x. So my final answer is 5x times the fourth root of 2. Okay, so this one, we're going to do the same thing. So there's a lot going on here. So the factor of 54, that's the biggest perfect cube, is 27. So 27 times 2, and then I'm just going to rewrite these out. Okay, so 27, the cubed root of 27 is 3. So that's going to come out. That's not going to be underneath there anymore. But I have this that's in there. So remember what I always ask myself. So 3 goes into 3 evenly one time. So it's going to come out as x to the first, or just x. So I'm done with that. 3 evenly goes into 6 2 times. So it's going to be y squared. So I'm done with that one. And 3 goes into 4 one time. So I'm going to pull out a z to the first. But then I have kind of, if you want to think about it as a remainder, I have a remainder left over as 1. So I'm going to have a z to the first left over inside. So let's see. Let's clean this all up. So I have 3xy squared z times the cubed root of, let's see what's underneath here, 2z to the first, or just z. So that's it. Okay, so when we are multiplying radicals, what we're going to multiply the outsides together. So like if I had a number like 3 and 7 on the outside, I would multiply those together and then multiply the insides and see if I could simplify. So that's where we're going to start. So I don't have anything on the outside here. So on the inside, I'm going to say 6 times 2, which is 12. Then I'm going to see if I can simplify. So it kind of becomes a problem like this. So does 12, does it have a factor that's a perfect square? And it does. It has a 4. So the square root of 4 times the square root of 3, and the square root of 4 is 2. So 2 times the square root of 3. Okay, I'm going to do the same exact process here. So this is 27. And so I'm going to ask myself, well, what's the cubed root of 27? 27 makes a list, and it's 3. These are going back on those properties that we talked about yesterday. So when you multiply, you add their exponents, but yesterday the bases were the same. Notice today the exponents are the same. So we're going to treat this a little bit differently. So instead of like adding the exponents are going to stay put. So we're going to look at this as 5 times 3 to the 1/4 power. So we're going to kind of go backwards, and because if we went, if we use that property and we went forwards, then we would end up with 5 to the 1/4, 3 to the 1/4. So we're just going to pull that 1/4 out and look at this as a multiplication problem of 5 and 3. So my final answer is 15 to the 1/4 power, Or don't forget, you can write it like that. Either way is just fine. Okay, so this kind of becomes like those first two. So if I multiply 12 times 18, I'm going to get 216, and 216 actually makes the perfect cube list. It is 6. Okay, and so this is the first one that, the first time I have things on the outside. So 8 cubed root of 108 times 4, which is 432. And so I'm going to ask myself, okay, what is the biggest factor of 432 that is a perfect cube? And it's 216. So 216 times 2. And so when I take the cubed root of 216, that becomes a 6. And whenever this comes out, you're going to multiply these together. So my final answer is 48 times the cubed root of 2. Okay, let's do this one. So 2 times 4 is 8. And then times the cubed root of, is this the same problem? Okay, it's the same problem. Never mind. Okay, so let's go back here. So adding and subtracting radicals. We are going to look at this as like combining like terms. So like if we have, this is what we're used to. So if we have something like this, we know that we really can't do anything with that 7y. So we're just going to say like 7x plus 7y, and we're done. Same thing with this. So notice that I have the same type of root, so with the same index. So square root, and then I also have 2 underneath the radical for both of them. So these become like terms. So then I'm going to have 7 square root of 2. Notice that doesn't change, just like those didn't change, plus 7 square root of 3. So let's kind of look through what we can simplify, what we can't. So notice that these we can simplify. So it just becomes 10 square root of 3. These we can simplify. So it becomes 3 square root of 7. Same thing here. Notice same root. No, not the same root. So we cannot simplify this. So that cannot be simplified. Let's go down here. So now we have the same root. So I have -4 minus 6 is -10 fourth root of x. Okay, so notice these are different. So I cannot simplify them, but here's the thing. I can simplify this radical, and I can simplify this radical. So let's just look at the square root of 27. So it's hiding a perfect square of 9 times 3, and this becomes a 3. So if I were to rewrite the square root of 27, I would have 2 times 3 square root of 3. So this whole thing becomes 6 square root of 3. So we're going to do the same thing over here. So 75, that has a factor that's a perfect square of 25. 25 times 3. The square root of 25 is 5. And so we're going to multiply those together. So I have 20 square root of 3. So now notice I have the same like term, if you will. And so then I'm going to combine them. So 26 square root of 3. I'm going to give you a little hint. A lot of times, if you kind of use this as your guide, because I have a feeling that my answer is going to end up something like this with like a coefficient on the outside. So what I'll do is I'll take 54 and I'll divide it by that and see what happens. So 54 divided by 2 is 27, and lo and behold, 27, that is the perfect cube that I'm looking for. So just kind of a trick. So 27 times 2 minus the cubed root of 2. So the cubed root of 27 is 3. So I have 3 cubed root of 2 minus the cubed root of 2. So just as I thought, if nothing there, simplify to 1. So my final answer is 2 cubed root of 2. Okay, so at first, like division is very much the same way, but division, so like as far as like dividing outsides, dividing insides, and simplifying, but make it work to your advantage. So like when I see this, I could either look at it like this or look at it as 12 divided by 3. To me, it's in my best interest to look at it like that because 12 divided by 3 is 4 and the square root of 4 is 2. This one, I don't like to look at it like that because I can't do anything with it like that. But if I look at it as separate, then I can take the square root of 4 and the square root of 9. So it just simply becomes 2/3. This one, I think I want to combine them. So let's see what happens. So I have 15x to the 7th over 5x. Yeah, so I can simplify those. So 15 divided by 5, that's 3. And I have x to the 7th on top, x to the 1st on bottom, so I have an x to the 6th. And then I can simplify that further. So I can't take the cubed root of 3, but 3 goes into 6 2 times evenly. So I have an x squared that comes out. So I have x squared times the cubed root of 3. Okay, so this one is a little sneaky because I can technically simplify it, but I really like it this way, and I'm going to show you why. And I think when you become more comfortable with these, you'll be able to see it. So I want you to notice this right here. So that simplifies out to 2 because the cubed root of 8 is 2. So I have the cubed root of 6 on top over 2, and I am good with that. Here's the thing, you want to avoid any kind of root in the denominator because then you'll need to fix it later. So anytime I can get rid of a root in the denominator, I call that good. So let's do this one. Let's think about 192 divided by 3. So I'm just checking to see if that is helpful or not. And it is actually. So 192 divided by 3 is 64, and the cubed root of 64 is 4. Notice how this has different roots. So I don't like it like that. So I think what I'm going to have to do is put it in terms of a rational exponent. So I have y to the 4/3 power over y to the 5/7 power. So don't forget that we can kind of go back and forth and have it kind of help us. So I have y to the 4/3 minus 5/7 power, and do the math on those fractions, and you end up with y to the 13 over 21 power. Whew. Okay, now let's talk about when you have to have something, some kind of root in the denominator. So you've actually had this before. So I'm just going to give you an example. What if we have that? You knew that you had to get rid of the square root by multiplying it by itself. And what happened is it became the square root of 25, which is 5. So it got rid of that square root. And so we ended up with 3 square root of 5 over 5. Okay, so we're going to do that same type of thing for these two problems here. So same thing, I'm going to multiply by the square root of 7 this time. And so notice this is 49 and the square root of 49 is 7. So notice how that stays consistent. And then I have 2 square root of 7 on top. And notice rationalizing the denominator, basically at the end of the day, you cannot have a square root in the denominator. So it just gets rid of that square root. So you can multiply by everything in the denominator, but that 3 is okay. I don't really care about that. So I'm just going to multiply by the square root part of it. So on top, I have 4, and then I have square root of 2 times square root of 5, which is square root of 10. And then on the bottom, I have square root of 5 times square root of 5, which is 5. So I have 3 times 5, which is 15. Okay, we have 2 more, and these are a little bit trickier. So again, the name of the game is getting rid of the square root. So if I just multiplied by the square root of 5, I'm going to end up with a square root over there. So that's not going to be helpful. So this is where you have to multiply by a conjugate. And so what conjugates do is they're going to get rid of our square root for us. So first of all, a conjugate just changes the sign of this. It's not the opposite. So notice that my -1, that stays put. The only sign that it changes is what's connecting the two terms. So if this is a -1 minus square root of 5, I'm going to have a -1 plus square root of 5. So whatever I do on the bottom, I'm going to do to the top, -1 plus square root of 5. Okay, so this is what's going on. On the bottom, I'm going to show this the long way, and then we can kind of shortcut it from here on. So if I were to FOIL this, I have 1, and then I have plus square root of 5, and then I have minus square root of 5, and then I have negative square root of 25. So let's clean this up a little bit. The first thing I want you to see is that these are going to cancel out. They will always cancel out. So I have 1 minus square root of 25 is 5, and so I'm left with a -4. So what I want to point out with conjugates, and we've talked about this before, is that inner and outer term will always cancel out. So all you have to do is multiply the first terms together and then the last terms together, and that is our way of getting rid of the square root in the denominator. So on the bottom, all that work, I ended up with -4. And then on the top, we're going to have a square root, and that's okay. So I'm just going to distribute that -3. So this is my final answer. Over here, so first of all, like step 1, you need to kind of figure out what the conjugate is. So the conjugate is 5 minus square root of 2. And then, so I'm going to come down here and put the equal sign. So let's do the bottom first. So I'm going to multiply the first terms together, which is 25, and the last terms together. So I have minus, because I have a positive and negative, square root of 4, which is 2. And then on the top, I'm going to distribute that square root of 5. So I have 5 square root of 5 right there, and then minus square root of 10. So let's clean it up for our final answer. So 5 square root of 5 minus square root of 10 over 23, and we are done.